So go to 227, go to the Statistics Online transition. This is why I've been putting all the updated material. Will I reorganize all this one day? Might be soon. And I'll put that there, and I'm looking for over here. This is what we're going to go over. This here, box plots and what? Skewness. So this is what we're going to work on, some box plots. Now, box plots are amazing. They're very fundamental in terms of, it's another picture of data called a box plot. And we're going to go over all of this. And it's a very common picture. Very often they use box plots to compare data. And so that's what was important to me to get all this out. So we're able to study box plots and do some work with box plots and everything. So here we go. There's where we're at. So let's look at the box plots here. Let me scroll in. There is a way to scroll in. I don't know what happened to it. We'll just have to do this. Okay? So we're going to start to ride on this. And essentially, here's the deal. Here's what we're going to do. You guys are going to love this. I know I do, but box plots and the distribution of skewness. Remember, what kind of skewness did we have? Left skew, what else? Right skew and normal. Okay? And then there's another kind of category where it's kind of inconclusive. So just because you have what's called skewness of data doesn't mean it has to be left, doesn't mean it has to be right, doesn't mean it has to be normal. There could be neither of all those things. Okay? So we're going to study really the box plot, how to do this. And this is what I'm saying here. You have these different situations here. But how you begin to draw a box plot, it's a very simple picture. You always need the what? 5-number summary. So you're going to need to find that in your TI. Okay, you guys know what I'm saying? We've went through that. You guys have procedures. You guys know how to do it. You can do that in your TI. The 5-number what? Summary. Okay? And what do box plots do? They're useful to provide a visual summary of the data, enabling researchers to do what? Quickly identify summary values, dispersion of the data, see how it's kind of, the dispersion of the data, and any signs of skewness. And so if you guys notice, you say, what is it? You got a 5-number summary? Yes. What is it? Well, you got to have, remember this, the minimum value. What else do you have? The first quartile, the second quartile, the third quartile, and then you have the maximum value. Okay? So you guys already know this. Is that true? You know, what's the first quartile? Let's see if you guys remember. First quartile. What's the definition? Isn't that the what? 25th percentile? What's that? What does the 25th percentile represent? It's the value that separates what? The bottom 25%, because those are the numbers that are less than it. So this is why I say here, ladies and gentlemen, between the minimum value. Now, you say, what's the minimum? In this picture, the minimum is what? 4. What's the first quartile value in this picture? 6. You need the real number line. 25% of the data is between 4 and what? 6. Okay, you guys okay with that? And then what's the second quartile value in this picture? 7. Good. What do you guys know? What percent of the data is between the first quartile and the second quartile? It's another 25%. You say, why? Because the definition of the second quartile is the 50th percentile. So 50% of the data, 25 and 25, is below that value. This is also known as your what? The median. Okay, and then what's the third quartile in this picture? It's 8. 25% of the data is between what? The second quartile and the third quartile, meaning 25% of the data is between 7 and 8. And then finally, 25% of the data is above the third quartile, and it's between 8 and what number? 8 and what? 10, the maximum value. So what you guys are seeing here is a summary of the it's a 5-number summary, and it's really a description of your distribution here. Because you call this thing a box plot. Where is the box? The boxes are here. And then you say, well, what's this line here in green? What do we call these? It's really known as a box and whisker plot. Sometimes they should call them box plot for short. Box and what? Whiskers. I don't know why whiskers. Box and whiskers is a box plot. You have a left whisker. This is where the left whisker is. Okay, that green line is called a whisker. You have a right whisker. That green line is called a right whisker. Okay? And again, you have the box in the middle, and ladies and gentlemen, this is called a box plot. And I did give a summary for you guys here, right? You should already know this stuff, the summary. The minimum score, you guys know the smallest data value. But it says that they are excluding what? Outliers. Good. And we're going to talk about that. Anybody know what an outlier is, by the way? You guys know what an outlier? No? It's okay if you don't. We're going to talk about them. No, actually, it's outside another interval, and we're going to see that. It's outside an interval. But think of an outlier as a data value that is kind of far apart from all the others. It's a data value far apart from the others. They're called outliers. It could be far above or far below, but it's far apart from the rest of the data. Now, how far apart is defined, and that's what I mean. It's going to be in a particular, outside a particular interval. Of course, they call that the lower quartile value. This is also known as your what? Q1. You know, this is your Q1, by the way, lower quartile. And you know, 25% of the data falls below the lower quartile value. This is known as a first quartile. Oh, I did say that. So the lower quartile also is known as that first quartile. And then the median, oh, you guys know that's the second quartile. 50% of the data is below the median value or the second quartile, 50th percentile. And that's pretty much what it says here. The upper quartile is Q3. And then the maximum score, again, that's the highest score, excluding outliers for the most part. And, you know, it's shown at the end of the right whisker. So this is what they mean by that. It's over here and over here, the what? The maximum score and the lowest scores in the 5-number summary. And this is just a graph of it. And ladies and gentlemen, this is called a box plot. Okay? Now, the idea of an outlier, does anybody know? Their outliers sometimes are thought of as, like I said, these are values that are what? Far away from the rest of the data. And it's kind of analogous to something like, sometimes people feel that there's people who are outliers. You know, like maybe Bill Gates, although I'm not a big fan personally. Maybe Elon Musk. I'm not a big fan either of that guy either, but, you know. Who's the Apple guy? Steve Jobs? I'm more of a fan of Steve Jobs, personally. Thought of as outliers, right? People that are far away from who? Everyone else, okay? You guys want to think of it that way. But we're really talking about data values as an outlier. Now you say, what does it mean to be an outlier? Well, if you take, again, here's what the deal is. An outlier is a data value that is numerically distant from the rest of the data set. That's pretty much what I'm saying. Now, how far does it have to be? It has to be outside the whiskers of a box plot. Outside the whiskers? Yes. You say, what's a value outside the whiskers? Well, any data value that would be kind of like this. Over here, over here, over here, over here to some degree. It's outside the whiskers to some degree. Okay. But really, the definition is you take the first quartile value minus 1.5 times the interquartile range. Do you guys remember what that interquartile range is, by the way? I gave you the definition. Let me get rid of all this distraction. What's the interquartile range? We can find it in this picture. IQR. Do you guys remember the definition? Interquartile range, ladies and gentlemen, IQR. What is it in this picture? It's going to be what? Q3 minus Q1. It's this length right in here. So you're going to take 8 minus 6. What's 8 minus 6? 8 minus 6, ladies and gentlemen, what do you guys think that is? Very simply, 8 minus 6 gives you what? 2. So your interquartile range here is the value what? 2. All right? Easy breezy, lemon squeezy? Okay. Now, let me remind you guys, if you said, what interval are they talking about? Do you know what Q1 is? What's Q1? And I think I should rather have used the blue color. Tell me what Q1 is and Q3 is. It's 6 and it's 8. Is that true? Okay. My interquartile range is 2. So remember this. This will be 6 minus 1.5 times 2. And the other one would be, oh, what was the other? 8. 8 plus 1.5 times the interquartile range of 2. So if you said, I want to know what a data value is that could be considered an outlier, it has to be outside of this interval. Here's what I mean. I'm going to go up here and clear out my calculator. And I'm going to say I need 6 minus 1.5 times 2. And that gives me what? 3. And then what is 8 plus what? 1.5 times 2. And that's 11. Okay? All right. So here's what I'm saying. Any data score that's outside this interval will be considered an outlier. And that's by definition. This is what I gave you guys right in here. So yeah, you need that interquartile range of what number? In this example, 1.5. And if we color coordinated this a little bit differently, I don't know if I want to do that. Maybe Q1 is in pink. That's 6. And then I'll get purple maybe. Q3 is 8. Okay. So you guys can... Oh, pink and purple. You guys can verify by the colors. 6 and what? 8. Okay? But it has to be outside what number? 3 and what else? 11. So it has to be outside. So 3, ladies and gentlemen, let's kind of find a color for the outliers. Has to be outside over here. Outside has to be smaller than 3, a data value, and bigger than what number? 11. Okay? So this is where the outliers will live. That's what they're saying. So you say, well, what's the story? We have no data. Well, you're going to see where I got my data. I don't think we have any data values that are outside. So that's why there's no outliers in this example, but you'll see that. We'll see that. But that's kind of the idea behind the outlier. If you have any datas out there, they're called outliers. And then sometimes you want to include the outliers and sometimes you don't. A lot of times people throw out the outliers, okay? Because they're thought of as being what? These very, very extreme values. They're not even, this is not Z values and unusual values. This is different. It's kind of like throw out the Steve Jobs and the who, the Jeff Bezos and the who else? What do we say? Elon Musk and what's the other one? Bill Gates. Throw them out. What happens if you don't have them? You just have the normal people, I guess. Normal data. Okay, you guys see what I'm saying? But that's kind of where the outliers would live, and that's how they compute that. Anyway, here's my point. You know where I got this data, by the way? Because this is a special picture. This picture, just so you guys know, let me start to get into the skewness of things. I want you to pay attention to what's called the symmetry. Okay? What is symmetry again? Do you guys know? This is like symmetry. See that left whisker and the right whisker? They have the same length, do they? Don't they? So they're kind of symmetric. So the left whisker and the right whisker are symmetric. I'm even going to point this out, that the distance between Q1 and Q2 is the same as the distance between Q2 and Q what? 3. So this is a picture of a box plot that is symmetric. Okay, there's some symmetry there. The distance, the left whisker in terms of the distance is the same as the right whisker, and the distance between Q1 and Q2, or I'm sorry, Q1 with Q2 and Q2 with Q3, those distances are also the same. So this is symmetric. That's an important detail for box plots. Because where I got this data was right here. This is the data set I used to compute or to create my box plot. Notice, there are no data values that are smaller than 3. And there are no data values that are above 11. That means there's no outliers. Okay? That's a, huh? You did? You found a phone. Oh. What do you do with phones when you find them? Huh? What do you do? You what? Oh, that's a good idea. Where's my phone? All right. It's all right. Just so you guys know, there's no outliers because this data was from the past example. All right? That's why it's important. You know, that's why you say, oh, okay, I'm going to look at that interval, no outliers. So here's what you guys want to know how to do, right? To draw a box plot, first of all, what do you have to do? You're going to use the TI calculator to get what? The 5-number summary. In the TI, your 5-number summary is right here. Do you guys remember? It's the minimum, it's the first quartile, it's the second quartile, also known as the median, third quartile, and the maximum value. So here's the 5-number summary. That's exactly what we had in that first picture. Okay, just to let you guys know, that's exactly it. Now, here's the idea. I want you guys to know Desmos. Has anybody ever heard of Desmos by any chance? Do you guys like Desmos? I love Desmos. Oh my God, I love Desmos so much. It's a free graphing sort of calculator, kind of. It's free. You get it online at desmos.com. There's even a free app, Desmos app. I have it on my phone. I love it so much. It's on my phone. It's on my iPad. It's even on my computer. I think I even sent you guys. It's a link probably in your somewhere. So here's what I want to show you guys. You guys already know what a histogram is, right? It's a bar chart. But how you handle in Desmos, you put histogram and then you put this parentheses, and then in square brackets, this is what you put the data inside in Desmos. That's all these data values that I have up here. So I put those data values in the histogram in Desmos. I put my bin width to be 1 for my histogram, and I said, you know what, count is a frequency, by the way. And then I said, align the bin in the center. So I created a what? Histogram, because I want you guys to see how histograms and box plots are related. Guess what Desmos also does? It draws a what? Box plot. And again, you enter the same data that way. You got to use that square bracket. And then you say, throw out the exclude means to throw out the outliers. It doesn't matter because there were no what? Outliers anyway. So there's no outliers in this example. So it wouldn't matter. Okay? Whatever. But very often you do exclude outliers. Sometimes you want to see them and sometimes you don't. So anyway. Okay. And so in Desmos, guess what happens? This is the histogram. And this here is the what? The box plot at the bottom. Okay? Do you guys remember when we discussed histograms? What does it mean? What is this a picture of when we talked about this? How does your data, what does that mean? Where's most of the data? It's in the center. If most of your data was in the center, what do we say about the distribution? Most of the data is in the what? In the center. What do we say? Distribution was what? Normal. So ladies and gentlemen, in terms of the histogram, I make the claim you guys already know what this looks like. This is the normal what? Distribution. Most of the data is in the center. And it's actually centered about the mean and the median. The mean here was 7. Just to kind of go, see this here? You guys see that? It happens to also be the what? The median. And it has to also be the mode. The mode was 7, the most popular data value. So now I want to focus on the box plot and the observations here, just so you guys know. Take a look at the whiskers. You see the distance here for that left whisker and the right whisker? They're the same. They're equal. That's going to have some meaning. You see the distance here between the first quartile value and the median, and the second quartile value and the median. You see that distance? They're also equal. So what do you think that means when these distances are equal? It means there's some symmetry properties here, symmetric properties. That means the left portion is symmetric to the right portion. Is that true? And when you see that, what do you think we say? Most of the data is in the center of your histogram, and the data is considered to be symmetrically distributed. The left whisker and the left box are the same lengths as the right whisker and the right box. Therefore, the distribution is symmetric, which is known as what? Being normal. So when you have this symmetry, when the distances are the same like that in your box plot, we say this represents a normal what? Distribution. That's what we're looking at right here. Okay? Normal distribution. Most of the data will be in the center. And that's what I want to notate. And then notice the relationship between the mean, median, and mode. They're the same. And when you have that, that's a normal distribution. That's a trait for a normal distribution when they're equal. Now, be careful. This is all approximately, even though in this example they're exactly the same, but if they're super close to each other, even though they're not exactly the same, could still have a normal distribution. Just to let you guys know. This is not, depends on being close and what close is. So this is a normal distribution picture for a box plot and for a histogram. All right, what do you guys think? Is that pretty nice? All right, why do we care about these? We get to actually see the distribution and various relevant values instantly by a box plot. Now, you know what I did here? I asked the same question again, but this time with different data. I said, okay, how much sleep did you guys get last night? For me, it was 0. But this is the data that was gathered. What happened with the TI calculator and the 5-number summary? Well, the mean was 6.1, by the way. And then here you go. This is your 5-number summary. Is that true? And then I summarize it here. Here's the 5-number summary. I got that in the TI. You guys know how to do that. And then, you know what I did? I did the same exact thing. I entered this way. Make sure you put the parentheses in the bracket for a histogram. Make sure the bin width here is 1. And the count is frequency. That's the bar height. I centered the bin alignment is at the center. So I created a histogram. I created a box plot. Notice what I did down here. This is important. I offset it by -1. That just means shift the box plot down 1 unit. Then I had a height value of 1, I guess. That's all that means. And I didn't click exclude the outliers. That means outliers are included. Okay? So when it's not checked, that means to include the outliers. They may be some, they may not be. So what will happen is it'll show it if there's an outlier. But I don't think there is. Now, remember when we talked about histograms? What do we say this picture looked like to us? We talked about distribution in histograms. You guys remember? What do we say about that? Yeah, but what else? Where's most of your data? Most of the data is on the right. What do we say that meant? Yup, that meant a left what? Skew situation. Here's how you can think of it, right? Think of the normal distribution where most of the data is in the center. This picture is like they're pulling the distribution to the left. They're pulling those bars to the left. You guys see what I'm saying? The bars are being pulled to the left. That's a left skew distribution. Focus on this left whisker in relation to the right whisker. Which whisker is longer, the left or the right? Good job, left. Now focus on the distance between the first quartile and the second quartile, and then the second quartile and the third quartile. Those distances in that picture as well. Which distance is longer? From here to here, which is really up here to where? Up here. Which distance is longer? The left. Is that true? You guys see that? So here's my point. When you see this phenomena, that the left whisker is longer and the right distance there, let me say that again. The left whisker is longer, and then the distance between Q1 and Q2 is longer than the other side. You say that this distribution is what? Left what? Skew. That's my point. This is the picture of a left skew distribution. This is the observations I said here. Most of the data is to the right in your histogram, and the data is considered non-symmetrically distributed. It looks like the data is pulled to the what? To the left. That bar, those bars, like the histogram's pulled. Therefore, it is what? Left what? Skew. Okay? The left whisker in the left box is longer than the right whisker and the right box in the box plot. This indicates a left skewed distribution when you see this situation. Okay, you guys see what I'm saying? Left skewed. Notice this also, that the mean is smaller than the median and is smaller than the mode. These are the values here. So this is another classical trait, but it's not written in stone, but it's a classical trait of a left skewed distribution. Well, just kind of, not always, but, you know, because sometimes it depends on how close the values are. So you guys okay with that? You guys see what left skewed means? Easy breezy, lemon squeezy? All righty. Whew. Now we have what? What is this? The green data. How much sleep did you get last night? Hopefully some. Here's the data in green. Use the TI-84 calculator to determine the what? 5-number summary. Okay, here we go. We sure did. Here's the 5-number summary. 2, 3, 3.5, 4.5, and 7. I put it down here as well. Okay? All in the what? The TI calculator. All right. Guess what we did with Desmos? Exactly the same thing. We created a box plot and a histogram in the same way. The bin width was 1. The height of the bars is the count. That's frequency. And you center the bin box plot. We offset it by -1 with a height of 1. We exclude the outliers. You exclude outliers. That means a no. That means the outliers are included. Just because you include outliers doesn't mean there are some. Okay, some data has outliers, some don't. It's by that same computation. All right, what do you guys see here? What does that picture look like to you? Most of the data is where? Is on the left. So if you said to me, what did that mean for histograms? That meant it was what? Right skew. But if you considered a normal distribution where the data is on the center, this what they want to remark about is it looks like you're pulling this histogram to the right. It's being pulled to the right. That's why it's right skewed. Let's look at the what? The box plot. What do we notice? Let's look at the whiskers. My left whisker length versus the right whisker length. What do you guys notice? Yeah, right whisker's longer. Is that true? And then what about the median to the third quartile? Isn't that longer than the first quartile to the median? So here's what I want to say. This tells me it could be a right skew. This tells me also it's a right skew. So it looks like in terms of this is not symmetric, these lines. You say symmetric about what? About the median value. So it looks like the right side lines are bigger than the left side. What does that mean? Your data is right skewed. Okay, the right lines are bigger than the what? The left lines. That sound pretty simple? Right skewed data. Now, I do have the summary of the observations as well, saying most of the data is to the right in your histogram, and the data is considered a non-symmetric distribution. It looks like the data is pulled to the right, therefore it is a right skewed situation. The right whisker in the right box is longer than the left whisker in the left box in the box plot. This indicates a what? A left skewed distribution. And what you should see, traditionally speaking, is the mean is bigger than the median, bigger than the mode, and it is. 3.9 versus 3.5 and 3.3. So that's a pretty good picture. Doesn't always happen, but that's pretty good. All right, you guys okay with that? And so, oh, I think I have a typo here. You guys see the typo? Right, something's wrong. Right skew. I got to fix that when I get home. Typo. Good job. And I'm like looking at this. I'm like, you know what's another simple thing is you see these inequalities? They're pointing to the what? To the right. You guys see that there? And like up here, the inequalities are pointing where? When you look at the mean, median, and mode, inequalities are pointing to the what? To the left. It's the left skew, generally speaking. Just want to make sure that you guys have that observation. It's kind of interesting. And then I did it again. You say, what did I do? Well, what are they saying here? Here's your data. It's in red. I gathered data. And yeah, the mean is about 5.5. Okay. But here's your 5-number summary. And, you know, I summarized it here. I did the same thing in Desmos. I said, hey, you know what? Put the data in Desmos as a histogram and as a box plot with the same frequency, center, offset by -1. This box, it doesn't matter whether you click it or not. It depends. This said exclude the outliers, but if they have none, you guys know, it depends on whether you have them or not. Whatever. Okay. Let's see what happened. Let's study this situation, ladies and gentlemen. If I said to you, where's kind of most of the data? It's kind of hard to see where most of the data is. You guys agree with that? It's not clearly to the center. It's not clearly to the left. It's not even clearly to the right. Is that right? You guys know what I'm saying? And then let's check the whiskers. What would you might say? What are the whiskers suggesting? The left side is longer than the what? So you're going, this might be a left skewed distribution, maybe. But then what do you notice? You may notice something else. What's going on here? Yeah, look at this. From the first quartile to the median value versus the median to the third quartile, the boxes are suggesting what? That the right side is longer there. Is that right? In the boxes. So this is not very clear like the other examples. In fact, this is kind of contradictory, don't you think? So you say, well, what does it mean? It means we kind of can't really say left skew or right skew. It's kind of inconclusive. Or even center for that matter. It's clearly not symmetric, but you're having an issue. So that's the observation. The data almost looks uniform. It's not, and there's no symmetry that can be observed. The left whisker is longer than the right whisker, but the right box is shorter than the left box in the box plot. This indicates a contradiction, and we cannot conclude any symmetric or non-symmetry aspects to the distribution. Therefore, we have an inconclusive graphical description of the distribution. Notice something bizarre, too, that the mean is bigger than the median, which is smaller than the mode right in here. 5.5 is bigger than 5, but they're both smaller than 8. This is kind of a contradictory situation. You know, when it's equal, normal. When it's left, left skew. When it's right, right skew. Generally speaking. Not always. You got to look at the picture. All right. Now, here's the deal. Why did I say originally, why do we care about box plots? Because they give summaries of the distribution and we can actually compare now data sets. Very often, we like to compare data sets because we like to compare groups of data. Like, for example, in this case, this is real. This is kind of the relationship, ladies and gentlemen, between the number of children mothers have and what? Their education. Whose mother? Maybe I should say grandmother, because you know when this study was done? 1953 in the American Journal of what? Sociology, 1953. Boy, that was a long time ago. All right, let's see what this said. What are they saying here in this? It says, the following data sets represent the number of children for two separate groups of mothers. Those who are considered not educated, no more than 6 years of education. What does no more than 6 mean? Oh, you guys know, 6 or less. Good. And those who are considered educated, at least 7 years, okay? They're talking elementary school, middle school, high school, college. So the question is, really, is there a relationship between education of a mother and the number of kids they have? I don't know. What do you guys think? Don't know. Isn't that kind of an interesting question? No? Anybody grandmother has a lot of kids? Whose grandma has a lot of kids? I don't know. I really don't know. One. I don't know. I don't even know what a lot is, but that's a good question. What is a lot? Some grandmothers have 14 kids, 12 kids, 10 kids. Imagine that. Anybody have more than that? Anybody grandma has more than that? Who has the record in the room? Should we gather data? Who has the record? Whose grandma has the most kids? We might have to gather data. I've been asking that kind of question for years. I think the record I've had was at about 14 kids or something. I think I said that, and then somebody said, no, my grandma has like 18 kids or something. Ooh, man. Well, your great-grandmother had a lot of kids? How many? 18. You guys see what I'm saying? I'm not making this stuff up. 18 kids. Nice. I don't know. That's a separate question. I never asked the education. I just said, how many kids, right? 18. Wow. Darn. Imagine coming up with 18 names. What do you name them? 18 names. Or, I don't know. Was any of them named the same thing twice? No? They all had different names? Kind of like George Foreman 1, George Foreman 2. You have kid 1, kid 2, kid 18. I don't know. I would run out of names. Anyway, when was this study in? 1953. Let's see what's going on with those moms, right? So look at I put the data in blue. This is the less educated in blue. Okay, see the data values? Right, what are the data values? 14, 13, 14, 14, 10, 2, 3, 5, 0, 0, 13, 3, 9, 2, 10, 11, 13, 5, and 14. So, ladies and gentlemen, I think this is real data, by the way. And then the mothers who were considered educated, that means they had at least 7 years of school. What was their data? Ah, there it is. I can do this. Look at these numbers. What are these numbers? 0, 4, 0, 2, 3, 3, 0, 4, 7, 9, 1, 9, 4, 3, 2, 3, 2, 16, 6, 0, 13, 6, 6, 5, 9, 10, 4, 5, 4, 3, 3, 2, 5, whatever. And then they have another 15 here, right? Okay. So in this example, you're computing the 5-number summary in the TI so that you can construct what? You're going to look at the box plots now because we're going to compare box plots. And I put in blue, the box plot in blue. That's the least educated mothers. And then here's the most educated mothers. All right. And now, here's what we're doing. Let's take a look. This is the whole idea of really creating box plots, so that sometimes what you can do is compare data sets visually rather quickly. All right, you guys with me on that? Oh, and in both situations, we didn't throw out the outliers. So the outliers are included. It just means that they may not be any outliers. Okay, so we included the outliers. Oh, look at my offset, by the way. You know what that offset means for the blue? It means it just shift the picture up 3 units. And this one is shifted up only what? 1 unit, okay? In case you guys were wondering about that. Anyway, and you say, oh, there you go. See, it's at 1 and 3. All right. Let's see if we can draw any conclusions about this. How do we want to compare? First of all, this is number of kids, right? So I would do this. I would say, you know what? In blue. Would you guys say that's a left skew or a right skew situation for the top one? I'd say it's left skew. And then you say, why is that left skew? Well, I guess we have blue here. Let's do this. That line seems to be bigger than what this line. Is that true? And what else? This line seems to be bigger than this line. So for the whiskers, the left wins out. For within the box, the what? The left also wins. So that's why I can say, this is left skew. All right. So it means most of the data is on the what? On the right side. Is that true? Most of the data is on the right. So what does right correspond to? That's like number of kids, because the median value in this picture, the median value is what? For this is 10. Is that true? So in blue, that middle median equals 10. Let's compare it to the other distribution. And when we see the other distribution, we say, okay, here's my left whisker. Oh, but the right whisker is what? Much bigger. So I'm going to say that right whisker wins out. You guys okay with that? All right. Now, let's take a look at what you have here. This distance and this distance seem to be what? They look to me to be kind of equal. Is that right? So I would say there it's kind of inconclusive. But since the right whisker's longer, what can we say? Distribution is what? Also right skewed. So they both have a right, not also. This is a right skewed distribution. That means most of the data is on the left side. Okay, you guys with me on that? Let's compare the what? What's this value down here? This is going to be what? Looks like that number is what? 4. So for the green data, ladies and gentlemen, that green data, the median is 4. So let's see if we can think about what this might mean for us, right? The more educated you are, most of the data is on the left. That corresponds to having less what? Children. Is that true? And in fact, the median value is 4 compared to the least educated mothers in blue. You know, the most of the data is on the right because it's left skewed. So that is like having more children. And that median was what? 10, ladies and gentlemen. You guys see my point? So 10 versus the other one is what? 4. And so I would say this looks like, yes, the least educated mothers are having more children. The more educated mothers are having what? Less children. Does that make some sense? See how we can compare box plots pretty quickly here. And so let's take a look at the guidelines for essentially comparing box plots, right? I put that there. I said this. Compare the respective medians to compare location. Compare interquartile ranges, the box lengths to compare dispersion. That is right in here, the IQR, right? So when you're talking about dispersion here versus down here, dispersion. Which has a greater dispersion? Which has the bigger interquartile range? The blue, isn't that those lines bigger? So that means the data is more dispersed. That's the dispersion. And that's the uneducated mothers. So that has a greater dispersion there than the educated mothers have a what? Smaller dispersion, interquartile range. That's why you compute it. And that's what they want you to do too. They want you to compare the interquartile ranges, the box lengths, to compare that dispersion. Look at the overall spread by the adjacent values next to them. Look for signs of skewness. We did, and look for potential outliers. Well, they didn't have any outliers. You thought they may, but there is none because it would label them, and you don't have any, data values that are outliers. So there are no outliers for these pictures here. Okay, but box plots, there's no outliers for these. I'll share with you pictures where they have outliers. But box plots are very good at, ladies and gentlemen, starting to compare data values and very good at trying to compare data sets and just get a general quick picture of the distribution. Okay, what do you guys think? Was it worth staying up all night and not sleeping? Just for you? Are you worth it? Are you guys worth it? Maybe. I hope. If you don't believe that, you're never going to think that. You're never going to know that. Of course you're worth it. Right? You never want to take an I remember, my daughter once told me, because my daughter finished a math degree at Cal Poly. I have a daughter, Ashley. Anyway, one of the best compliments I've ever had in my whole life, because she sees me working at home, She just watches me, just looks at me. Like, what are you doing? And she said, you know what, Dad? And she takes a look at what I'm doing all the time. Says, you know what, Dad? I wish I had you for all my classes. Started thinking about that. I said, oh, yeah, that would have been nice. I think she's giving a compliment. What do you guys think? And she's at Cal Poly. She's, I'm not going to say it. I don't care. Who cares? She used to come home mad sometimes. Or actually, part of that was on the pandemic even. Because she hated going to school during COVID. Probably like a lot of people. And she was at a university, right? She's at Cal Poly. She gets so mad. She'd come home. She'd say, Dad, or not even come home. She'd be sitting in another room. She'd come out of her room angry. Said, Dad, those instructors are lazy. She's furious. Lazy instructors. God, I hate these lazy instructors. They just do PowerPoint presentations and go do the homework on the platform. You know what I mean? Whatever that publisher provided, and it's wrong. Damn, these instructors are lazy. They read somebody else's PowerPoint. I was listening to her, and I'm like, oh, that's too bad. That's kind of messed up. It makes me laugh because I understand. Because I know, yeah, you can have some instructors that, I don't know, they just take the publisher's PowerPoint and they go over it. I don't know. And they say, okay, here's your homework platform. Good luck. You know, the publisher's platform stuff that you pay a lot of money for that's buggy and doesn't work. Horrible. She hated that situation. I said, well, sorry. I also included a kind of a math-ish example. It's not even a math-ish example, in all honesty. You know, this stuff that we do, you know, math people get criticized by some of the other disciplines, and it's all baloney, and I know it's baloney, right? It's baloney. I can share with you how I know. And I won't mention names, but okay, I'll mention it. You know, there's other statistics courses that are offered in the school, and one of the things that they say to the math people for why they want to justify it is because, oh, a lot of your examples are just, they're not just unique to our discipline. We want to talk about what? Mothers and kids that they have. You know, it's relevant to our discipline. You, on the other hand, you get to talk about all these weights and widgets of stuff like that, right? We don't like those examples. Therefore, we need to teach our own version of statistics. You're like, really? Are you serious? This reminds me of one of those kind of questions because sometimes people don't like these questions, but they're important. This is what I mean by that. Share with you guys what I mean. You know, sometimes there's various health issues that people can have. And you get old enough, you're going to get a health issue. Okay, you're going to have something happen. Trust me. I used to be a young man once. I was Superman back in the day. If you guys don't know. I could go without sleeping for days. Didn't even need it. I was strong. Oh, you guys don't know. I was Superman. I remember when I was even younger, I had 3 jobs, ladies and gentlemen. And, you know, 3 jobs. Not 2. I think I maybe had 4. Let me count. Well, some of them were part-time. There weren't 3 full-time jobs, but I had like 3 or 4 jobs. 1 full-time, a couple of part-times, 2 or 3 part-times. And then on the weekends, you know, I actually worked on a Saturday. On Sunday, you know what I did on Sunday? No. I got up early on Sunday to do the laundry. I did it for my... Am I being recorded? I did it for my ex-wife, my 2 daughters, and me. So I got up early on a Sunday to do what? Laundry. Then I did grocery shopping for the week. I didn't have a day off. And you guys know what? I was strong. I didn't even need it. I was like, I'm good. And then as you get older, what happens? Your body wears down. You wear down. And it's not the same. So now I get to really sound like an old man. I was carrying these heavy things probably about 2 or 3 months ago. I can't remember. Stuff I used to carry all the time easily. And the next morning I woke up, couldn't even lift my arm. It was my left arm. I couldn't even lift it. It's like, what happened to my left arm? I can't lift it. And thank God I wrote with my right. Couldn't lift my left arm. I don't know what I did. I might have torn a rotator cuff. Just by carrying things I used to carry. You know, they're kind of heavy, but I used to do it, you know. So your body's not the same. So anybody else here Superman? You guys think you're Superman? No? You might be, but give it some... I know you are. I do. I believe you. I know it because I used to be it too. And then I used to listen to my grandfather talk about getting old. And I never used to listen to him. It's like, whatever. You know, whatever. Not going to happen to me. Yeah, happened to me. Happened to me. Like, oh, hey. Anyway, why am I telling you guys this? Oh, because I had no sleep. But guess what, ladies and gentlemen? There are some issues idiopathic respiratory. I think I misspelled respiratory. I got to go back and fix that typo. Respiratory? I don't know. It might be respiratory. Distress syndrome, whatever that is. And the birth weights. So they are, infants that are born with these certain conditions. And then there's corresponding weights they have. They weigh them. And guess what the deal is, ladies and gentlemen? These are birth weights in blue. It's the birth weight of infants with SIRS who died. All these values. And then they're going to compare that to the birth weights of infants with SIRS who did not die. They what? Survived. You guys see what I'm saying? These are some very relevant, meaningful kinds of examples. These are relevant. This is good stuff still. It's meaningful. So I don't know. Maybe you're into sort of nursing, or you're into sort of the health sciences, or maybe you're into sort of an area where these have meanings. But like I said, you're going to see in some of those courses these kind of scenarios, this kind of data to compare. You're going to see some box plots. So what I did is I created the box plots for you guys and reminded people of the guidelines. And there's the guidelines. There's the box plots, okay? So just looking again, let's talk about some skewness, right? Because the blue is they died. Let's put that there. I'm just going to go straight to the point. These infants died. They both have SIRS, and these infants survived. Couple of things to note. This point down over, I can't even see. Down there versus this point where? Over here. You guys see what I'm saying? So you can start to compare the median values. The birth weight of those who died is less than the birth weight of those who what? Survived. You guys see that there? You guys see my point? You can find the value. You can approximate the value. You could use the TI to get the values, But these are like the median values, so you guys can see that there. Okay, let's do green. But the important thing is you guys learn how to read this. So the birth weight of those, these are the median values. These are the ones, the adjacent values you want to compare. So, you might say, you know what, if an infant that is born with what, SIRS, the birth weight's going to be a factor. Let's see the skewness of this, right? We have the left whisker and the right whisker. We also have the left length of the box and the right. Oh, in both cases, what's the deal? The right side is longer here. The right side is also longer here. What are we going to say? This is what? Right skewed. So the distribution is right skewed. Most of the data is on the left. So not only, ladies and gentlemen, is the weights smaller for those who died, most of the weights are even to the left of that value. You guys see what I'm saying? That's how you think of that. Wow. So you want to give, like remember we were talking about the dog, your dog, and the doctor said what? You want to make sure the dog gained some weight. There's probably reasons for why weight is an issue. Kind of just looking at the data. And then what about this one here? Just kind of curious. What would you say about the distribution here? You got the left whisker, the right whisker. Which one is longer, you guys think? I think the right whisker might be a little longer. It looks like they could be about the same. I'd have to look at the numbers, but okay. But let's look at the box. What do you guys have here? The right certainly is longer than the what? And the left in the box there, right? So guess what I would say? They're both what? Right skew. I would think that it would have been that then most of the data is on the left. I would think it would have been left skew because, again, survival and more weight, but not necessarily. And then you want to look at the dispersion, the interquartile range here and over here, the dispersion, IQR in blue. Which lines do you think are bigger? This is all just a visual without even computing the values. Just giving a quick visual. Which one is bigger? I think the survive looks a little slightly bigger. So what does that mean? A bigger dispersion. It looks like the weights are just, are what? They're distributed with a bigger range there. The ones who died have a smaller range in terms of the weights, looks like. And they're centered around that value, probably about 1.5 kilograms. You know what I mean? Versus the ones who survived are bigger than about 2 kilograms. So weight, weight is a factor. But this is how we start to compare the data. So, it shows that the median births, if we look at the conclusion for comparison and location, shows that the median birth weight of the infants who survived is greater than those who died. Okay. The interquartile ranges are reasonably similar. They kind of look similar. That's true. So the overall range of the data set is greater for the surviving infants. The batches, both set of data appear to be right skew. And the batch of the infants who died are slightly more skewed than those who survived. Okay, I believe that. Slightly more skewed. Yeah. The skewness is not particularly marked in either case, but okay, that's what they're saying. Yeah, both skewness are positive. That's another way of saying right skewed. Outliers. Neither data shows any outliers. General conclusion. The batches of data look as if they were generally distributed in a similar way. That's true, somewhat right skewed. But with and then the interquartile ranges are kind of similar, but with one batch located to the right, larger location to the other, you can see immediately that the median birth weight of the infants who died is less than the lower quartile of the birth weights. Now, they're actually doing that too. They're saying this. That median value down here is smaller than the what? This first quartile of those who survived. So this is why you actually look at this as well, the first quartile. So this is what they're saying as a general conclusion here. Okay, you can see immediately that the median birth weight of the infants who died is less than the lower quartile of the birth weight of infants who survived. So it looks as if they can safely say that survival is related to what? Birth weight. Okay, so you can see how comparative box plots, blah, 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 give a compact, quickly assimilated summary of the data, suggesting that infants who survived and infants who do not may typically have different birth weights. And that might seem to you boring and too math-ish, but I would say, very useful knowledge. Very useful, okay? Especially if you're thinking of any sort of health issues. Useful. If you're going into those things. So, yes, we care about mothers and education. That's not an issue. We like those kind of examples. Is that true? But data is data, and I would recommend to you that when you start to even read the book that I have here, assigned to some of those questions, it's all good. That you learn a lot about data and statistics just by reading the question and the phenomena that they're describing. And I never knew about this SIRDS, but it's good to know. And I think all the data is good to know anyway. So that's why I stood up just for you guys to do some what? To get some nice sort of work on box plots and outliers and yada, yada, and worksheets and solutions, not just for you, but for some of the other classes I have. They have their work too, But anyway, what do you guys think? Is that okay? It's on my website. You guys can download this for yourself. Okay. And then we're going to take a quick break. And then I'm going to show you guys how to use Desmos to do some of this. What do you guys think? Is that pretty fantastic? All right. I'm excited. I'm glad I showed up today. even though we had a hard time. Let's get the clock out. Let's give you guys a break here. All right. All right. See you guys in a few minutes. Anyway, let me think about that. Okay. Let's gather some data so we can show you guys how to use this stuff, and then you can do your homework and whatever. What kind of data should we gather? That's the problem. Let's gather data on a question like what? Something interesting where you could get kind of some good numbers. Not sleep data. How many? It's a girl question? Well, guys, actually, I hate to say it, there are guys. Okay, I like that question. It's a gender, what the deal? Gender what question? How many pairs of shoes? Because there's guys who like shoes. It's a gender neutral question. Thank you. How many pairs of shoes do you own? We should go around the room. Okay, let's gather some data, and I know you may have to think a little bit. So how many pairs of shoes? Let's start here. Start to the left. How many pairs of shoes do you own? That's okay. How many pairs? 17. Good. I like that number. How many? 7. How many pairs? 8. All right. How many pairs? 10. How many pairs? 10. How many pairs of shoes? 25. Ooh. How many pairs of shoes? 7. How many pairs? 12. How many pairs? 20 plus. I don't know. Say 20. Okay. How many pairs? Okay. We'll say 25. How many pairs? Okay. How many pairs? The gentleman back there. 10. How many pairs?
7.
How many pairs?
15.
How many pairs? Behind you. How many pairs? Hey, Hannah, how many pairs do you have? Good, Hannah. I like that number. She has 4. How many pairs? 11. Okay, and then 2 more data values. How many pairs? 8. How many pairs? 2. How many pairs? 10. That's such a great question. How many pairs of shoes do you guys own? Good job. Okay. So let me kind of go through this idea for us, what we've been doing. So note here, I'm going to actually get the mean standard deviation, and I'm going to use the what? TI 84 plus CE. Okay, how many pairs of shoes do you own? A great question. So let's go to the TI here, because it's a good way to review some of these things as well. And I'm going to go stat. No. Stat, edit, edit. So we're going to enter this data, right? So I'm going to scroll up. I'm going to clear that out. Okay, I thought I cleared it out. Hit clear. Come back down. All right, so maybe we'll have to scroll in a little bit here. So there we go. That might look okay. Okay, let's enter these data values, okay? So I can share with you guys how to do that. 17, enter. 7, enter. 8, enter. 10, enter. 10, enter. 25, enter. 7, enter. 12, enter. 20, enter. 25, enter. 6, enter. 10, enter. 7, enter. 15, enter. 4, enter. 11, enter. 8, enter. 2, enter. 10, enter. Okay? So remember, we entered data here. Now what I'm going to do is I'm going to hit stat, calculate one variable stats. So I want to share with you guys again how you go about this so that you guys can what? Answer some of those questions here. Now, remember, typically I'm going to go to the mean and standard deviation to the tenths. So what do you guys see there? What is that going to be? 11 point what? Is it 2 or 3 to the tenths? 3. Outstanding. And then your standard deviation, what's that going to be approximately here? 6 point what? Yeah, 6.5. Outstanding. Good job. So, you know, generally, if this was like computing z-values, you guys know what I mean? You would do this. You want to get these. So I just want to kind of review that here because we're also going to use the mean and we're going to try to look at the skewness of this. Whatever. So this is kind of a standard thing to do. Now remember, you also want to do this because you need the 5-number summary. So if you're going to do a box plot, and that's the whole idea, you need the 5 what? Number summary. So remember the definition. It's the minimum value, the first quartile, the second quartile, the third quartile, and it's the maximum. So, all right, let's go do this here. Okay? So 2 is the minimum. What's the first quartile? 7. What's the median? Second quartile. 10. What's the third quartile? And then the maximum value is 25. So I want you guys to know that drawing a box plot does require the what? The 5-number summary here. Okay, so you guys have that 5-number summary. You're using the definition, and there you go. Now, what you would do, and this is why I'm using software, because really you would want like graph line paper to some degree, and maybe we'll do that. Okay, so maybe just to kind of give you guys the general idea here. Or maybe we can't, because you know, you guys want to note the range. We don't have 23 lines. But anyway, whatever. We don't have 23 lines. So here's what I'm going to have you guys do. I was going to kind of share with you guys how to do it on like graph paper. But we'll use what? We're going to use Desmos. And what you guys can do is graph this on your own, desmos.com. I think I might have even have that in your homework. I have that link. So let's find Desmos. And you know what? I actually have it here. Let me do this. I'm going to clear this out. Remove the trigonometry stuff. Okay. So I think what I mentioned online is to draw both a histogram and, you know, box plot. So let's do that. go here, function. And if you said, where's that histogram? Here we go. Histogram. And so notice what it says here on the left. It says they want the data set. So you're going to have to put the bracket. And you say, where's your bracket? Right here. And now you get to hit the data set. But you guys are going to have to tell me tell me the data so I can enter it in, because I can't go back in and look at it. I can do it sort of. I can do this. Let me go to the browser here. I can do it this way in the browser. You go, oh, here's my Desmos. Okay, we can do it that way. So let's draw a histogram just to go through it. Bless you. And then we need the parentheses here. And now it wants the data set. So, okay, so I'm going to hit bracket. And what I'm going to do now is I'm going to go back on my iPad and just look at all the data values I had. What was the first data value? 17. Hit a comma. And then what? 7, comma. Then a what? 8, comma. 10, comma. 10, comma. 25, comma. What else? 7, comma. 12, comma. 20, comma. 25, comma. 6, comma. 10, comma. 7, comma. 15, comma. 4, comma. 11, comma. 8, comma. 2, comma. And 10. So notice what I just did. Okay, and I kind of don't like using that. I'm going to change the color. Change the color there. So here is, if I can, I'm going to try to. Here's what I mean about the formatting. I'm going to shrink this. On the x-axis, I'm going to go from like 1 to, all right, maybe 18. Maybe that's helpful. And I'm going to change my bin width in this example. So you say, how do you go to the bin width? You got to go all the way up here after the data set. It kind of shows you down there. Oh, no. Do I put that? Yeah. Bin width, I'm going to change. I hit the bin width. I'm going to put the bin width to 3. Or let's do the bin width here. If I can do that. Yeah, I can do a bin width 3. It's at the center. Maybe we'll do bin width of, oh, come on. I mean, once you enter it, you can't go click that again. We're going to go back here and change the bin width, okay? Let's see what 2 looks like. About 4. Yeah, bin width of 4 might look okay. Spread that out. There we go. That kind of looks a little better. Okay. And then I'm going to scroll out so you guys can see the details. So apologize there. And if I want to change the height, well, anyway, I'm going to leave it that way. Now, that's not a box plot, but I'm going to copy all this data because I don't want to do it again. So I'm going to go copy all the data values. Edit, copy. And now we're going to put box plot. So put box plot and parentheses. Once you do that, you have to put the square bracket and then you paste this in. Okay? Now I'm going to offset this because you say, I'm looking at it right now. Yes, offset it, put -1. And we're going to include the outliers. Now you might say, Mr. Judge, where are the outliers? Well, there is none in this picture. Let's see if I can do this here. I'm gonna change this format for the y values. The y values, that's to put like -2 up to 10. Maybe that will be a little bit better. All right, you guys can see that there? Okay, so we are looking at both of these things here. Now, I wish I can, maybe I can. I'm going to do this here. I'm going to take this picture. Let me see if I can share that, bring it into the iPad. So I'm going to have to go with that picture. I have to do a send. You guys remember how to do that? I'm going to send it to my iPad. I want that picture. Yeah, I don't have a... There should be where... Oh, I know what I'm going to do. I'm going to do it this way. Maybe open in preview and share it that way. Yeah, I'm going to do an airdrop. Yeah. Yeah. And add to the existing note called what? Box plots. Okay? All right. There we go. So, done. There we go. Anyway. Try to see what I can do. It's like I want to just do this. Okay. All right. Now, so ladies and gentlemen, we have the 5-number summary. This is the box plot. Let's see if we can answer some questions. Okay. First of all, let's notice, what's the minimum value here? What is it? 2. This is going to be 2. Okay? And then, what is the first quartile value? 7. See, how do I know? It's right here. So this is going to be where 7 would be. And then notice where 10 is. 10 is right here. Is that right? 15 would be here. That's the third quartile value. And then 25 is the maximum. So the maximum is out here. So if you really wanted to color coordinate it to see it, minimum value is the 2. Okay? First quartile is the 7. The median value right here is 10. Third quartile value, pink maybe, here. And then the maximum value over here. So you're looking at, you know, the box plot. You're looking at that 5-number summary. And all right, so we know some things about this. So let's ask you guys about the distribution. What would you guys say? Is that left skew, right skew? What do you guys think? Is it normal? I'm going to say this. Take a look. It's going to be, notice this. The right whisker is a lot bigger than the left whisker. And then this right distance from the second quartile to the third is a lot bigger than the what? So yes, I'm going to say what? Definitely looks to me like it's what? These right values are, these lengths are bigger. Is that right? So this is a right skew distribution based on everything we just did. So most of the data is on the left. And, you know, there's your box plot. Down here, this is right skew. Okay, you guys okay with that? Now, there's no outliers. Now, you might say, how do I know there's no outliers? Well, let's go back to that interval question, because it was a question somebody asked in the break. The reason there's no outliers is because decimals will show you, that it will plot the outliers, and you would see it. But how do I know for certain there's no outliers? Well, here's what we know. We need the interquartile range. The interquartile range, by definition, is Q3 minus Q1. So it's going to be 15 minus 7, which is known as what? 8. So in terms of the colors, Q3 minus what? 7. Here's a 7. What's that? Isn't that 8? You guys okay with that? Now, you say, why do I need that? Well, remember the definition here? It's going to be an interval. The interval from Q1 minus 1.5 times that interquartile range, Q3 plus 1.5 times the interquartile range. Q1 was orange. We know that value. That's 7. Is that true? So I just want to let you guys know, I'm going to verify this. 7 minus 1.5. What was that interquartile range for this? So that's your 8 here. And then you got Q3, which was pink. So Q3 we know was 15 plus 1.5 times interquartile range of 8. So from those of you guys who are really interested in that computation for the outliers, you know, if there were outliers, decimals would show you. So I know there's none, but I want to verify that and show you guys what I mean. So we're going to quit that. We're going to do this computation. 7 minus 1.5 times 8. 7 plus 1.5 times 8. So -5 to 19. Double check. Do we do everything okay? Uh-oh. Oops, sorry. I made a mistake. That's where it is. Here you go. 7 minus 1.5 times what number? 8. And then it's going to be 15 plus what? 1.5 times 8. 27. Okay. -5 up to 27. So you might say, hey, Mr. Judge, what is this? Well, any data value, you know, this is that interval. If you're outside this interval, you got to be outside, smaller than -5, but bigger than 27. You got to be outside. If you are, then you're an outlier. And if you look at the data values, none of those data values are what? The biggest you have is 25. The smallest you have is 2. So none of the data values are outside, right? This is what I mean. This is a different interval, kind of. What is it? -5 to 27. So here's my -5. Here's 27, okay? You have to be outside here, these numbers. You got to be to the right here and to the left here as a data value. This is not unusual. This is not our z-values. This is where the outliers would live. And so, to let you know, none of the data values that we have up here are outside that interval. So that's why there's no what? Outliers. Just so you guys know. Okay, so your 5-number summary is going to be used to create the box plot. You guys can copy that picture from Desmos for your homework. Okay? Because really, you really want graph paper to really do this picture. And, you know, we don't have the graph paper. I didn't go through how to do it by hand. You can read about that in your book. I'd rather you look at that in Desmos. That's what I showed people. And remember the median value with this. Let me find another color. Not blue. Oh, it's green. It's 10. So that's pretty much what we talked about today. Is that right? You guys know what I'm talking about? But that's kind of, if you go back and you look online, now we can talk. Yes, there's Desmos, but now I can talk about this. Remember I said I gave you guys homework that used this stuff? Right? It's called box plot and 5-number summary. They asked for the mean, standard deviation, the range, largest value minus smallest value, 5-number summary, interquartile range, Q3 minus Q1. Draw a histogram with a bin width of 10, a box plot in Desmos. Ask it's left skew, right skew, normal. I should put also inconclusive. What are the outliers, if any? You can say none, or you can list them. Now, let me go back and remind you guys. What did I also do for you guys? I did the solutions. So there is your histogram and the box plot. That looks like left skew to me. No, maybe not. Maybe not. Maybe. I don't know. There's no outliers. This one, there's a histogram in the box plot. Histogram and box plot. And maybe you said, you know what, Mr. Judge, I think I want to see some outliers. What would that look like? Let's go back to Desmos. Not sure, but let me do something like this, okay? I'm going to say somebody had maybe 48 shoes. Do I have any outliers? Does Desmos show me that even if it's 48? Maybe not. That's certainly right skew. Ah, there we go. There we go. Sorry. See that 48? In Desmos, you see this little dot over here? That 48? Guess what that is? That's a what? That's an outlier. So when I added that number, that's an extreme value. Like if somebody came in and said, like the ex-Mrs. Judge, yeah, I got 48 pairs of shoes. This month only? This month? 48? She would be an outlier in terms of shoes. So what are they saying? This is the box plot you have, right? But you have to exclude that 48. It's labeling the outlier. So this is your box plot when you throw out the 48. So that you guys can see that little circle is a box, is an outlier. All right, you guys okay with that one? What do you guys think? You guys gonna get the app in Desmos? It's free. You can even get it online. I have it on my phone. I play with it at night. So you guys can use this to do your homework, and that was the whole idea. So anyway, ladies and gentlemen, let's take a look at here. Where are we at? Come on, where are we at? There we go. Oh, you can't see the outlier. Oh, there it is. There's the outlier, the lower right. I want to fix it so you can see it. I'm not sure. There we go. Okay, so if you guys didn't see that outlier at 48 on the video, there it is. There's an outlier. Okay? It's that little circle. So they say throw it out. It's not in the data. It's thrown out. So anyway, ladies and gentlemen, I hope you guys enjoyed all the presentation and the work. You guys can do your homework now. And we'll see you guys in this room when? Wednesday. Okay, take care.